So let's look at the Michael addition and synthesis and work our way back to determine how this compound was synthesized. So here are the steps. Before we begin actually with the steps is that I want to warn you that you can use, the approaches here seem similar to the ones we use with Claisen and aldol. However, this OH is going to limit how we do it. So we need to be careful about that part, but we'll explain as we go. So first you have to break the beta gamma bond, put a double bond in the alpha beta position, and then put a negative charge on the gamma position. Okay, so if you look at this, you have two ways of numbering this. All right, so if we assume that this is our alpha, then this would be our beta, and then that would be our gamma. So you just keep counting alpha, beta, gamma. However, you can also make this your alpha. You can make this your beta. The beta didn't change, but the gamma would be now the alpha from the previous compound or from the previous structure. It's the same structure, but again, depending on how you view it. So let's take a look at this. So this, if we want to break the beta gamma position, or sorry, bond. So we break this bond and we would break this bond. So let's take a look at that. So if we break this, we would be left with the OH is the same, CH3, and then of course you have an enolate, negative. And then you would have the beta would be the CH2. Well, actually, let's just make it without the CH2. Right there. Or down here, it's the opposite. Remember the alpha beta. This is the alpha, that's the beta. It was the alpha beta on the other side in this one. And then of course you have a CH2. And that's our enolate. Okay. So once again, here's the alpha, here's the beta. You can think of this as the gamma. Here's the alpha, here's the beta, and this is the gamma. Oops, draw it like this. Okay, now there's a problem here. One problem is we've seen over a few lectures that you can't have an enolate with an OH. Okay, that is an impossible compound. So this one does not form. And as well as this one, if this one does form, guess what it will do? It will not attack the alpha beta unsaturated carbonyl. It will actually attack the proton. It will deprotonate. So this will deprotonate. So therefore, this strategy fails. So what you have to do is you have to think of, how did we do this before? How did we do it before? Well, remember, we had to use a stabilized enolate. We had to use a stabilized enolate. So let's look at then what we could be using instead. And then, okay, you might say, well, how do we form then this OH at the end? Well, this comes, and you should always remember that this comes from hydrolysis. So this is back to what we did in chapter 23. So let's look at the strategy A. Now, I'm only going to do strategy A. There was a strategy B, but I think this one works good enough. So what you have to do is you have to use actually, again, a stabilized enolate. And this is what you would use instead. All right, so this ensures that the CH3 is there. And remember, we can decarboxylate, get rid of the CO2, and then we end up with the desired product. So first, we have to do this. So then we would have to deprotonate. So we would do this. NaOET, HOET, and we would produce the following. Okay. And now what we can do is we can use this as a stabilized enolate, Once again, go back and look here. You can see that this is what we're looking for, a stabilized enolate, and it's basically this one with a CH3 attached to it. So we will use that with this right here. Right there. So we will use okay. Okay, now a word of warning here, just to help you out here. You can easily lose track of the carbon that was used to where it was bonded simply because you have big structures. So I also fell prey to this. So you have to be very careful and you have to keep track of that. So again, I like the highlighting. That way I can see what I did here. So right, great. So let's highlight that. Or you know what? Sorry, we use a different color for highlighting. Let's use a green for that. Okay, so we're gonna flip this, and if we flip it, it's going to look like this. OET, OET, and then there's this CH3. So I just okay. So now this is here's the yellow. And now you got to count how many carbons you have here. You have 1, 2, 3. And then, of course, the phenyl ring. So you will have one, here's 2, 3, and then the phenyl ring. And then always be ready to really flip rings and carbonyls. That's part of the game. We have to, so let me show you the connection here. Okay. Very well. So we attached that. And now remember what we need to do is we need to do hydrolysis. H2O. And then heat, or we could use, so this is the acidic hydrolysis, or you could use the basic, so the KOH, the H2O, the heat, that's the first step, and then the second step would be the acid conditions and the heat, and then this finally will cause decarboxylation, hydrolysis of the ester, and then you will end with the product that we made. So I will show you in a second, but let me draw the product. Obviously, that's the product that we made above. So let's actually make it above right there. So and right there. So we have okay, and let's highlight again where is the connection. So the connection is there. And this is your, nope, not that one. This right there. Okay, so let me just say one last thing before we continue. So when you do the hydrolysis, remember, with hydrolysis, these become OHs, become hydroxy group. So they become carboxylic acids. And then, so this is hydrolysis. And then the second step would be to decarboxylate. So we're just going to say decarbox right there. And then what happens with decarboxylation is that this, after it becomes an OH, is removed. Okay, this becomes CO2 minus the CO2. And then you would be left with, if this turned into an OH, here it is right there. Obviously, the CH3 is now switched down. That is it.